Hi there! In the previous videos you saw the t-test, where we tested the hypothesis that the expectation of a variable was equal to a certain value. A variant on this is a setting where we test whether the expectation of a variable in one group is equal to the expectation of that same variable in another group. In essence, this will follow the approach as in the t-test. So this technique is known as the two-sample t-test. There are two different cases though, the paired and the unpaired case. Let's consider the following example. This will be an example of the paired case, and you will soon see why. When using steel girders in construction work, it's important to know how much shear force they can endure. However, it gets quite expensive to test the strength on full-scale girders, so scale models have been developed. There are several methods to compute the strength, which can then be compared to the observed strength for these scale models. The ratios between the predicted and the observed strength for 9 of these scale models are given in the table for 2 of these methods, the Stockholm method and the Osaka method. Let's call these numbers xi and yi respectively. They are realizations of a vector of random variables, capital Xi and Yi. We assume that the 9 measurements are independent, and it seems reasonable to assume that the measurements have been performed with the same uncertainty. We want to test whether these two techniques are significantly different. As always, the null hypothesis will be the default state. So in this case, this means that the expectation of x is the same as the expectation of y. Let's call them mu1 and mu2 as is customary. The alternative hypothesis is that there is a non-zero difference. We do not specify which one should be greater than the other one, so we are working with a two-sided alternative hypothesis. As before, we want to decide which test statistic we are going to use. Well, since we are interested in the difference between the two techniques, it makes sense to look at the difference of the observations as well. For each measurement, we can look at the measurement according to the Stockholm method minus the measurement according to the Osaka method. Let's call this variable di, d for difference. Our hypotheses can now be formulated using the expectation of this variable d. Now, do these di follow a normal distribution? Well, with only 9 observations, we cannot expect the histogram to look very much bell-shaped. Let's take a look at the QQ plot. Not very convincing if you ask me. There exist tests which assess whether normality can be assumed. For this dataset, they tell us that normality is a fair assumption, so we are safe. We will not go into more detail about these tests here. Keep in mind though, if normality cannot be assumed, there are other tests that can be performed. However, for now we continue with the assumption of normality. Well, now we are again in the setting of a one-sample t-test. We saw that in this case we need to test statistic t, which is given by the mean of d divided by the standard deviation of d over square root of n, where t has a student t-distribution with n-1 degrees of freedom. In our case, we get a t8 distribution, and the value of the test statistic turns out to be minus 2.0985. We can compute the p-value as we did earlier, which gives p equals to 0.0691, indicated in orange in the sketch. Recall that we have a two-sided test, so we also need the right tail probability. Hence, on a 5% significance level, we would not reject the null hypothesis. In R, we would obtain those results again with the t.test command, now acting on the two data vectors called Stockholm and Osaka. We have to indicate that the observations are paired, and that we want a two-sided test. In the output, you notice the t-test statistic, the a degrees of freedom, and the p-value. Notice that a one-sample t-test on the difference Stockholm minus Osaka gives exactly the same results. I hope that by now you see why we call these observations paired. The measurements have been done in pairs. Each scale model was measured once using the Stockholm method and once using the Osaka method. Can you think of more real-life examples where you would need such a paired sample test? You can pause the video if you want to think about this. Well, here are a few examples. Measurements before and after some treatment, as long as you measure it on the same objects, are clearly examples of this paired case. Well, not all samples are paired though. Let's see if we can apply a two-sample t-test in the unpaired setting. We know that smoking has quite a lot of adverse effects. One of them is reported to be the decrease in lung function. Let's test this. We denote by X and Y the lung closing capacity for non-smokers and smokers respectively. Let's call the expected values of X and Y μ1 and μ2 respectively. This closing capacity is measured by having people exhale as deeply as possible. The closing capacity is then the air volume in the lungs, at which the smallest airways start to collapse. So ideally, this is as low as possible. Can you think of appropriate hypotheses? Well, indeed, the null hypothesis is that smoking has no effect. The expected closing capacity is then the same for smokers and for non-smokers. The alternative hypothesis, for which we seek evidence, is that smoking does have an adverse effect, meaning that the expected closing capacity is smaller for non-smokers than for smokers. μ1 is less than μ2. We have the following dataset. It contains the closing capacity for 725 people. 77 of them are smokers. Let's call this number N1. And 648 of them are non-smokers. This is N2. Do you notice the difference? In the paired setting, we needed two measurements for each object. For each girder, we had an observation for the Osaka method and one for the Stockholm method. In the unpaired case, there is no direct connection between the observations in one group and in the other group. As a result, it is perfectly fine to have different sample sizes for both groups. In our dataset, we find that the sample mean for non-smokers is 7.77. For smokers, it is 8.645. This seems to confirm our alternative hypothesis, but is this a significant difference? Well, let's investigate. First off, can we assume normality in both groups? For the non-smokers, this is clearly the case. For the smokers, the lower part of the histogram and the QQ plot do not completely behave as expected in a normal distribution, but not enough to reject normality. And actually, for large sample sizes, the central limit theorem tells us that the mean is approximately normally distributed, which is what we need. Hence, normality of the two variables is actually not needed if the sample size is large enough. Now, let's try to find a suitable test statistic. In the paired case, we could just take the difference for each observation and proceed by treating this as one variable. Well, this clearly doesn't work in the unpaired case. We can, however, consider the difference of the two means. Standardization of the mean of normally distributed variables gave us a student t distributed variable, both in the one sample case and in the paired two sample case that we considered just a few minutes ago. We always had to subtract the expectation according to the null hypothesis, and we had to divide by the sample standard deviation divided by the square root of the sample size. The hardest question now is, what about the standard deviation in our current unpaired case? Well, it turns out that we do get a student t distributed random variable if we use the so-called pooled standard deviation, SP, defined as you see on the screen. The pooled standard deviation is of course the square root of the pooled variance, which, as you can see in the top formula, is a weighted average of the sample variances in both groups. It can be shown that this is an unbiased estimator for the common variance. Note that this is actually another assumption. We assume that the variance in both groups is the same. We'll get back to this assumption at the end of this video. In the case where equal variances can be assumed, we end up with the test statistic t on the screen. It has a student d distribution with n1 plus n2 minus 2 degrees of freedom. Notice that here we didn't write mu1 and mu2. Indeed, this t has this given distribution under the assumption of the null hypothesis, mu1 equals mu2. Let's see what we get for our dataset. The pooled standard deviation can be computed using the definition that we just saw. Notice that it is indeed between the two individual standard deviations. All of this leads to the test statistic t equals minus 2.74, which is an observation from a student t distribution with n1 plus n2 minus 2 equals 723 degrees of freedom. Let's see if we can obtain this and draw a conclusion using R as well. The code is shown on the screen. The closing capacity for smokers was stored in the variable sy, the one for non-smokers in Sn. We are dealing with an unpaired t-test, and we assume equal variances. Our alternative hypothesis was that the closing capacity for smokers is greater than the one for non-smokers. As you can see, the p-value is 0.003. The reasoning always remains the same. This p-value is small, so if the null hypothesis is true, this is an extreme observation. It leads us to doubt the null hypothesis, so we reject it in favor of the alternative one, and we conclude that indeed, based on this dataset, the average closing capacity for smokers is higher than the one for non-smokers. But what about this assumption of equal variances? Well, there's another test called Welch's test, which can be used if this assumption of equal variances is not valid. The idea is the same, but the standard deviation formula and the degrees of freedom are different. In R, this test can be applied by setting the options var.equal to false. Were we to use it in this example, we would actually get an even smaller p-value and hence still reject the null hypothesis. Well, how do we decide whether we can safely assume equal variances or not? For large datasets, even slightly different variances may already be significantly different, right? Well, you may have guessed it, there is also a hypothesis test that tests whether the variances are the same. Here you see the R code and its output. It uses some test statistic here that a distribution we haven't covered. It's a Fisher or F distribution. But can you find out for yourself what hypotheses are being tested here? What is the null? What is the alternative? What is the conclusion? Well, I refer you to the Graspel questions after this video for the answer.